Good afternoon, good evening, everyone. So, today is the seventh week of this tutorial session on this course Principles of Modern CDMA, MIMO, and OFDM Wireless Communication. So, today we will solve some questions based on massive MIMO. So, first we will see some of the basic concepts. Just wait for 2 minutes. Little power issue is there. So, today we will study about massive MIMO, MIMO wireless communication, that is multiple input, multiple output wireless communication. So it is basically also called as MIMO system. So in MIMO system, at there is a transmitter antenna and receiver antenna. So first we will see at the transmitter side. Transmitter antennas are at the base station side. So there will be T transmit antenna, and R receive antenna. So there are multiple input like multiple transmit antenna and multiple receiver, that was multiple output. So this is RX receiver. So transmit antenna can transmit to any user. So here it can multiplexing can be done. So here let's suppose there are T transmitters. So the transmit symbols can be given as X vector, that is x1 x2 dot up to xt, and the received symbol vector, that is y bar, is equal to y1 y2 up to yt. So basically there will be a MIMO channel which will be used to which will be used for the transmission of this signal. So this This is transmitted through a MIMO channel and received at the user YR. So now what will be the size of this vector, that is MIMO channel H? So H will be of size of R cross T. So the dimension of this channel vector H is number of receive antenna cross T. So our channel vector H will be H11, H12, here HR1, HR2, HRT. So now we can simply write here that the received symbol Y1, Y2, YR is equal to the channel vector multiplied with the transmitted symbol X1, X2, XT. So, and there will be some noise associated with it. So we can write the noise associated with it, that is N1, N2 dot dot dot. What will the dimension of noise? H and T. So it will be NR, because total number of received signal is R. So at the receiver end, noise will be added. So the noise will be of R cross 1, and this transmitted symbol is T cross 1. The channel vector is R cross T, and Y vector is R cross 1. And also we can see this is multiplicable, because number of column in the first vector is equal to number of row in the second vector. So simply we can write Y is equal to Hx plus N, the noise vector. Just wait for a minute. So now the received symbol can be given as, let's suppose, Y1, that is the received symbol by user 1. This can be given as Y1 is equal to H11, we'll just multiply X1 plus H12 into X2 plus H1T into XT plus N1. So similarly, the received symbol YR is equal to HR1 X1 plus HR2 X2 plus HRT XT plus NR. So like this we can write. And there can be different variation of MIMO system, like single input, multiple output. So in single input, multiple output, there will be one transmit antenna and multiple receive antenna. And there can be also multiple input, single output. In that there will be multiple transmit antenna and one receive antenna. So today now we will study about the MIMO zero forcing receiver. So first, we will see, like when the signal is transmitted, like the signal vector x is transmitted, now we have to estimate that x. So in that estimation of x, how it can be done, so we will see that. So the equation is given as y is equal to hx. So this is just a linear equation. Here x is the like x1 comma x2 xt are unknowns, and so we need t unknowns are there, and there are r equations and r equations, because here you can see the equations are 1 to r. So in the simple scenario, when r is equal to t, then like in this case we can solve this matrix H, and H will be simpler. The inverse of the H matrix exists. So when r is equal to t, H is a square matrix and H inverse exists. So in this case, the estimated symbol x hat, that can be given as H inverse into y hat. And also there may be some case like when r is greater than t, this means number of receive antennas are greater than transmit antenna. So in this case, so our channel vector is r cross t, the transmit symbol is t cross 1, so our receive vector is r cross 1. So here H has more number of rows and column than column. So this is the H inverse directly does not exist. So for that we will see how like we can find the H inverse. So that we can find here comes the zero forcing receiver. But before that, let's see. Let's take a function fx that is equal to y minus hx square. So this is the error function, and the above error function is also termed as the least square error. So the resulting estimator is least square estimator. So our fx is equal to we can write this as y minus hx transpose into y minus hx. So this we can write yt minus what will be the hx transpose? It will be xt transpose into h transpose multiplied with y minus hx. So this can be written as y transpose into y minus x transpose h transpose into y minus y transpose into hx plus x transpose h transpose h into x. So this can be written as y transpose y minus 2x transpose h transpose y plus xt ht h of x. So I will directly write the final equation. So when we estimate, our x hat will be, as it is already derived in the classroom. So this x hat using the zero forcing receiver is h Hermitian into h inverse of h Hermitian y. So this is our FZF, that is zero forcing receiver. So zero forcing decoder can be expressed as x hat ZF is equal to h Hermitian h inverse into h Hermitian y, and we can write this as f of ZF into y. Also we'll see properties of this zero forcing. Like one of the property we can see properties of the zero forcing receiver matrix. So FZF into H will become H, like what is our FZF? That is H Hermitian into H inverse. Now we are multiplying this with one extra H. So let's multiply. So here we will get H Hermitian H inverse into H Hermitian into H. So this is the, like, see, this is matrix A and this is A inverse. So A inverse into A, what happens? It gives I. So this is one of the property, and but the converse is not true. Like let's suppose you multiply H of FZF. So this is not I. So here you will get H into, so this we will get. So this value is not equal to I. So this is one of the property. So basically the matrix H is invertible, that is the pseudo inverse is existing. So basically the FZF is the pseudo inverse of channel matrix H. So FZF, that is equal to H So this we can write as H inverse H Hermitian inverse into H of H. So this becomes H inverse. So basically FZF is the pseudo inverse of channel matrix H. So now we will come to our first question. Consider a symbol x1 is equal to 2 plus j and x2 is equal to 3 minus j. So the symbol x1 is given as 2 plus j and symbol x2 is given as 3 minus j. For an LMOT coded 1 cross 2 wireless system, the symbol vector transmitted during the second time instant in this system is given as. So the symbol vector transmitted during the second time instant in LMOT coded is given as. So this is taught in the class. It is basically minus x2 conjugate and x1 conjugate. So when we do the conjugate of x minus of x2, it will become minus 3 plus j conjugate. So it will become minus 3 minus j, and this x1 conjugate will become 2 minus j. So the correct answer is the option number B. Now coming to the next question, consider the MIMO channel matrix H is equal to 1 2 minus 1 minus 1 2 3. The channel matrix is given as 1 2 minus 1 minus 1 2 3. So now we have to find the corresponding zero forcing receiver matrix. So FZF is the zero forcing receiver matrix that is given as H transpose H inverse into H transpose. Basically you can write this when it is a real like when the channel is having the real numbers, but when its complex channel is there, in that case it can be written as H Hermitian H inverse H of H Hermitian. So it's in the real case we will find like this. So H transpose is equal to 1 2 minus 1 minus 1 2 3, and this is also equal to finding the pseudo inverse. So now our H transpose into H, that is given as 6 minus 1 and then plus 4, that will be 3 minus 3 is 0, again minus 1 plus 4 minus 3 is 0, 1 plus 4 5 plus 9 14. So this is our H transpose H. Now H transpose H inverse is given as 1 by 84 6 0 0 14. So this can be given as 1 by 14, 0, 0, 1 by 6. Sorry, here this element got uh, exchange in the H inverse, so it will become 1 by 6, 1 by 14. So now we have to find H transpose H inverse into HT. So this is basically our zero forcing matrix. So this will become 1 by 6, 0, 0, 1 by 14 multiplied with what is H transpose, that is 1, 2, minus 1, minus 1, 2 and 3. So we will get 1 by 6, this is 1 by 3, this will be minus 1 by 6, again it will be minus 1 by 14, 1 by 7 and 3 by 14. So this is our zero forcing receiver matrix. So in this question this is only asking, so which is the correct answer? That is option number C, I guess. 1 by 6, 1 by 3, minus 1 by 6, minus 1 by 14, 1 by 7 and 3 by 14. So this option is the correct option. Actually this is option number D. So this is the correct answer. Now before moving to the next question, we'll see some theoretical concepts. Like bit error rate for BPSK pencil got discharged, so let's wait for a couple of minutes, then we'll again start solving the question. And also this video will be recorded and link will be shared in the NPTEL portal. So now we will see how the bit error rate for BPSK with zero forcing receiver can be found. So it is basically the bit error rate with receive antenna using maximal ratio combining what we have studied in the week 4th or 5th. Just we have to substitute L is equal to R minus T plus 1. So that is the, we have to substitute that L value. So bit error rate for BPSK with zero forcing ZF receiver is equal to just 2L minus 1 CL, the same formula what we have used for MRC. Here substitute L is equal to number of receive antenna minus number of transmit antenna plus 1. So what we will get? We will get 2R minus T plus 1 minus 1 C R minus T plus 1 1 by 2 of SNR to the power of L. So here L will be also R minus T plus 1. So let's consider a small example. Consider 3 cross 2 MIMO system whose SNR is equal to 25 dB using the ZF receiver. Find bit error rate. So we have just studied the formula of bit error rate. Same we will use as for the MRC. Only thing is we have to use L is equal to R minus T plus 1. So average bit error rate is equal to 2L minus 1 CL 1 by 2 SNR to the power of L. Here L is equal to R minus T plus 1. So what is R? 3 cross 2 receive antenna is there. So R is equal to 3, T is equal to 2. So our L is equal to 3 minus 2 plus 1. So it will become 2. So now we have to just substitute the value of L here is equal to 2. So average BER is equal to 3C2 1 by 2 SNR to the power of 2. So this will become 3 factorial by 2 factorial, that is 3 into 3 by 4 into 1 by SNR square. Now SNR is given in dB. So is equal to 25 dB. So we can find that in normal unit log 10 log 10 SNR is equal to 25. So SNR is equal to 10 to the power of 2.5. So SNR will be 316.2278. Our bit error rate is equal to 3 by 4 into 1 by 10 to the power of 2.5 squared, because it was 1 by SNR squared. So it will become 3 by 4 into 1 by 10 to the power of 5. So it will become 0.75 into 10 to the power of minus 5. This we can also write as 7.5 into 10 to the power of minus 6. So we can see in the when the number of antennas increases, the bit error rate decreased significantly. So now coming to the question, third question. So consider a 5 cross 3 MIMO channel. So it is given 5 cross 3 MIMO channel with 0 forcing receiver. The SNR in dB required to achieve a given bit error rate is. So we have to find the SNR in dB required to achieve the given bit error rate. So here L is equal to R minus T plus 1, and also the bit error rate formula is same we will use. That is equal to 2L minus 1 CL 1 by 2 SNR to the power of L. So our L value is, here R is equal to 5, T is equal to 3 transmit antenna 3. So L is equal to 5 minus 3 plus 1, that is equal to 3. So bit error rate is equal to 5C3 1 by 2 SNR to the power of 3. So that is equal to 10 into 1 by 8 into SNR cube. So this will become 5 by 4 into SNR cube. Now what will be the value of SNR here? SNR cube is equal to 5 by 4 into bit error rate. So SNR is equal to 5 by 4 into 5 by 4 into SNR is equal to 5 by 4 into bit error in denominator, sorry, to the power 1 by 3, because this side SNR is in the cube. So now SNR in dB is equal to 10 log 10. SNR is equal to 10 log 10 5 by 4 bit error rate to the power 1 by 3. So this will become 10 by 3 log 10 5 by 4 BRDB. So this is the value of SNR for 5x3 MIMO channel. So the correct answer is 10 by 3 log 10 5 by 4 BR in dB. So option D is the correct answer for this question. So now we'll move on to the next question. Question number 4. Consider SNR in dB is equal to 30 dB, and this is a 1x3 MISO system, multiple input single output system. This stands for multiple input and single output system. So here 10 log 10 of SNR is given as 30. So SNR value is equal to 10 to the power of 3. So that is equal to 1000. Now it's asking the bit error rate with transmit beam forming is. So the bit error rate with transmit beam forming is same as MRC, maximal ratio combining. So bit error rate will be 2L minus 1 CL 1 by 2 SNR to the power of L. So here R is equal to C, R minus T plus 1. So R is equal to 1, T is equal to 3. So 2L minus 1 will be actually L will be 3 here. So L is equal to R minus T plus 1. So R is 1, 1 minus 3 plus 1. So here this will become minus 1. So when 2L minus 1 will become minus 2 minus 1, that is equal to 3. Minus 3. So we will take the positive value of L. So that is equal to 3 here. So we will take L is equal to 3. So bit error rate will become 5C3 1 by 2 SNR to the power of 3. So we will get 20 divided by 2, 1 by 8 SNR cube. So this is equal to 10 by 8 of SNR cube, that is equal to 5 by 4 of SNR cube. So now our SNR is 10 to the power of 3. So this will become 5 by 4 into 10 to the power of minus 9. So it will become 1.25 into 10 to the power of minus 9. So option D is the correct answer for this question. So now we'll move on to the next question. Question number 5. So it is given, consider total transmit power P is equal to 9 dB, noise variance sigma square is 0 dB, and 2 cross 2 MIMO channel is there with singular values 1 by 2 and 1 by 2 root 2. So singular value sigma 1 is equal to 1 by 2, sigma 2 is equal to 1 by 2 root 2. Okay. So now 10 log 10 P is equal to 9. So P is equal to 10 to the power of 0.9. So this value will become 8. And sigma square is equal to 0 dB means 10 log 10 sigma square is equal to 0 is implied that sigma square is equal to 10 to the power of 0. This will also become 1. Now the optimal power values for the two singular modes we have to calculate. So P1 is equal to 1 by lambda. So this will become, as taught in the classroom, P1 is equal to 1 by lambda minus sigma square by sigma 1 square. So this will become 1 by lambda minus sigma square is 1 and sigma 1 square is 1 by 4. So that is equal to 1 by lambda minus 4. And P2 is equal to 1 by lambda minus sigma square by sigma 2 square. This will become 1 by lambda minus 1 by 2 root 2 1 by 2 root 2 square. So this will become 1 by lambda minus this will be 4 into 2 8. 1 by lambda minus 8. So P1 plus P2 is equal to 2, that is given as 1 by lambda minus 4 plus 1 by lambda minus 8 is equal to 2. So it will become 2 by lambda is equal to 2 plus 12, so that is equal to 14. Is imply that lambda is equal to 1 by 7. Sorry, total power is given here 8. We have calculated total power is given as 8. So we will write P1 plus P2 is equal to 8. So this term will become 8 here. So it will become 8 plus 12, that is equal to 20. So finally we will get lambda is equal to 2 by 20, that is 1 by 10. So what will be the value of 1 by lambda? 1 by lambda is equal to 10. So now the P2 is given as 10 minus, like the value of P2 is 1 by lambda minus 8, as we have calculated here. So 1 by lambda minus 8. So now substitute 1 by lambda, that is equal to 10. It will become 10 minus 8, so it will become 2. And what will the value of P1? P1 is 1 by lambda minus 4. So P1 is equal to 10 minus 4, that is equal to 6. So what is the value of P1 comma P2? That is 6 comma 2. So the correct answer is option number D. So now we'll move on to the sixth question. Consider a 1 cross 2 multiple input single output system. So here it will be multiple transmit antenna but single receive antenna. With the channel vector H is given as H1, H2 and total power P and the noise variance sigma square. The output SNR for each symbol after combining in an LMOT coded system is. So this we have studied. The output SNR is given as half into mod of H squared P by sigma square. So the correct answer is option number D. Also we will see whether we can solve one example based on this. So let's solve one example. Consider the same example is here at the 9th, so we will solve there only then. No need to solve it again because we have the same example. In the question number 9. So first we will solve question number 9. So in question number 9, like it is given, symbol is given 1 minus 2j and the another symbol is given as H1 is given as, okay, this is not okay, that is a different question. So this is just a simple question as we have studied before. So this in this it is asking the considered symbol x1 and x2 is given as this 1 minus 2j and x2 is 2 plus 3j for an LMOT coded 1 cross 2 wireless system. So the symbol vector, so there is one receiver and two transmitters. The symbol vector transmitted during the second time instant in the given system is, so that we have already studied, that is minus x2 conjugate and x1 conjugate. So what will be the value? The symbol vector transmitted during second time instant is minus x2 conjugate x1 conjugate. So this will become minus 2 minus 3j and x1 conjugate is 1 plus 2j. So which option is correct? It's minus minus of x2 conjugate. So x2 conjugate will be 2 minus 3j. So minus of this will be minus 2 plus 3j. So option number C is the correct answer for this question. Coming to the question 8, consider a 4 cross 3 MIMO channel with zero forcing receiver. The dB SNR required for given bit error rate is. So we have to find the SNR in dB. So we have already found such question. So here L is equal to R minus T plus 1. So receiver is 4, transmitter is 3 and plus 1. It will become 2. So bit error rate is equal to 2L minus 1 CL 1 by 2 SNR to the power of L. So that is 3C2 1 by 2 SNR square. So that will become 3 by 4 SNR square. So what will be the SNR value? SNR value will be 3 by 4 into bit error rate to the power 1 by 2. Now we have to find SNR in dB. So SNR in dB is given as 10 log 10 3 by 4 bit error rate to the power of half. So it will become 5 log 10 3 by 4 into bit error rate. So is there any option? 5 log 10 3 by 4 into bit error rate. Option C is the correct answer for this question. Now coming to two theoretically question. The Lamoti coded code is orthogonal space time block code. So the option A is correct. Orthogonal frequency division multiplexing OFDM in a wireless system aims to overcome it aims to overcome the inter-symbol interference. So option D is the correct answer for this. And now we will solve one question. That will be the last question for today's class. The question is, consider a 1 cross 2 MISO system with y is equal to 2 plus j 1 minus 2j, or we can write here in terms of h value. Here h1 is equal to 2 plus j and h2 is equal to 1 minus 2j. So what is optimal transmit beam forming if channel symbol interface is available at transmitter? So for this question we can write y is equal to h1, that is 2 plus j, this is h1, 1 minus 2j, this is h2, into x1 x2 x vector plus w, that is a noise vector. So our x bar is equal to h1 conjugate h2 conjugate into 1 by norm of h into x. So the value of h1 is equal to 2 plus j and h2 is equal to 1 minus 2j. So the norm of h will be 4 plus 1 plus 1 plus 4. So this will become root under 10. So our x bar is x vector will be h1 conjugate, that is 2 minus j. This will become 1 plus 1 plus 2j into 1 by root 10 into x. So now y is equal to 2 plus j, 1 plus 2j into 2 minus j, 1 minus 2j, 1 by root 10 x plus w. So our y is equal to root 10 x plus w, and SNR will be 10 p sigma square, because that is equal to norm of h square into p by sigma. So today we'll end the lecture here only, and we'll meet the last lecture on the next Tuesday, and this video is recorded and will be uploaded on the YouTube. So thank you everyone for attending. We'll meet in the next class.